Good morning, dear students, and welcome to this moment's discussion. Today, we tend to continue our discussion on time series models. Particularly, we will be paying attention to moving average models. Do remember that in some of our previous classes, we already had introduction to moving average models. In some of our previous classes already, we had started looking at the moving average model of order 1. In moving average model of order 1, we looked at it in terms of 1, the model, 2, the mean of the model, 3, the variance of the model, 4, the autocovariance of the model, and then 5, the autocorrelation of function of the model. We equally had looked at the moving average model of order 2 in terms of these parameters mentioned in the moving average model of order 1. Today we want to continue our discussion by looking at the general model of a moving average model called moving average model of order Q, written in a short form as MA of order Q. MA of order Q, MA of order Q. MA of order Q, written as MA of order Q, MA of order Q. So we are going to look at this MA of order Q in terms of the following. One, we are going to look at the model. We look at the model number 1. We are going to look at the model of MA of order Q. We are going to look at what? The mean of the model of MA of order what? Q. We are going to look at what? The variance of the model of MA of order Q. We are going to look at, this is number 3, number 4. We are going to look at the autocovariance. Autocovariance of MA of order Q. We look at the autocorrelation. The correlation of MA of order Q. That's exactly what we are going to do in this discussion this moment. So we begin by first of all looking at how to write the model of MA of order Q. Do remember that in moving average models, it is a linear combination of the current time series to the previous error terms and the error term at the moment. A linear combination of the previous error terms of the series and then the error term in the current time. So if you are asked to write a model of MA of order Q, it is going to be written as this way. We have what? Y of what? Of t is given as, we have what? Mu plus. We have theta 1, A of t minus 1, plus theta what? 2, A of t minus what? 2, plus theta what? 3, A of t minus what? 3. Permit me to clean this. Plus, dot, plus, we have what? Theta what? Q, A of t minus what? Q, plus what? A of what? Of t. Where we have information that this A of t follows normal distribution with mean 0 and variance sigma squared of what? Of A. So this is how to write the model of a moving average model of order Q. Okay? There are Q up to the time t minus what? Q. Here is at the time t minus 1, previous error term, t minus 2, previous error term, t minus 3, previous error term, up to t minus q, previous error term. And then the error term and then the current time. This is how to write the moving average model of order Q. The first thing we say we are going to look at is the model, and the model has been written. The next thing is to look at the mean of the moving average model of order Q. When you are to find the mean of any model, what you do is to take the expected value of both sides of what of the model or both sides of what of the equation. So by taking the expectation, this is what I'm going to have. I have that E of y of t is given as E of this mu here plus this theta what 1 E of A of what of t minus 1 plus here is what theta what 2 E of A of t minus what 2 plus theta what 3 we have E of what A of t minus 3 plus dot 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 plus we have what theta what q E of what A of t minus what q plus E of A of t. This is what we are going to have when you are to take the expectation of the MA of order Q. And then, of course, we should know that given the fact that this model is a stationary model, you now find out that in the stationary model, the mean, the variance, and the autocovariance of the model are constant over time. In that case, the expected value of error term at t minus 1 is the same thing as t minus 2, is the same thing at t minus 3, and even it is the same thing at what at t, since they are constant over time. And then, of course, you know that we have been told that this error term follows a normal with mean 0. And of course, this mean that we are referring to as expected value. So by implication, the expected value of A of t minus 1 is 0, A of t minus 2 is 0, A of t minus 3 is 0, down to what to A of t. So in that case, what I'm going to have is therefore that my E of what y of t is given as expected value of a constant is a constant, so here becomes what mu plus every other quantity here becomes 0 because when the expected value assumes 0, multiplying with a parameter will make it 0. So all the quantity over here becomes what? 0, which implies that E of what y of t is given as what? As a mu. So the expected value of the model of MA of order Q is given as this. Okay? So we want to quickly go and look at the what at the variance. And by looking at the variance now, we might decide to drop this constant term here in this model, bearing in mind that the variance of a constant is what is 0. So permit me to clean here while we now write the model. So this time around, we want to look at the variance of what of the model. Looking at the variance of the model, and we are going to write this model this way, dropping the constant term in that model. So we have that our model becomes y of t is given as we have theta 1 A of t minus 1 plus theta what 2 A of t minus 2 plus theta what 3 A of t minus what 3 plus dot plus we have theta what q A of t minus what q plus A of what t, given that A of t follows normal distribution with mean 0 and variance sigma squared of what of A. Okay? When you are to find the variance of a model, what you do is to take the variance of the both sides of what of the models. And before we take the variance of both sides of the models, we are going to remind ourselves one thing that is a guide in taking variance of the sum of two random what variables that are not independent. If you are taking the variance of, say, variance of what? X plus what? Y. It is going to be given as variance of what? Of X plus variance of what? Of Y plus 2 covariance of X comma what? Y. This is what you are going to have. Okay? And in that note, what we are going to do now is to come and mimicking this expression, then take the variance of a model. So I am going to say that the var of what? Of y of what? Of t. Just like what I had here. When I had y plus what? X plus y, I took the variance of y, took the variance of what? I took the variance of x, took the variance of y before talking about the covariance. By implication, if I had x plus y plus z, I could have taken the variance of x, taken the variance of y, taken the variance of what? Z, and I'll begin to take the variance of the pairs of those random variables. That is now 2 covariance of x and y, 2 covariance of y and z, and then 2 covariance of what? Z and y. So what I'm going to do now is to apply it here now. So it is now going to be this equals. Here becomes what? Theta 1 all squared v of what? A of what? T minus 1 plus. We have theta 2 all squared v of what? A of T minus 1, 2 plus. We have theta 3 all squared v of what? A of T minus 1, 3 plus. Plus. We have theta what? Q all squared v of what? A of T minus what? Q plus. We have v of what? A of T plus. At this point in time, I am expected to begin to take the covariance of the pairs of the terms in the model. That is, by taking the covariance of what? Theta 1 A of T minus 2 and theta 2 A of T minus 2. But we should note that A of T minus 1 and A of T minus 2 are uncorrelated. So their covariance will exactly give us what? 0. The covariance of what? Error term, in fact, it is better I remind you this, that the covariance of what? A what? I, comma what? A j is equals to 0 for I not equal to what? J. I think it's better we give this expression. That the covariance of A I and A j is equals to 0 as long as I is not equal to what? J. And by implication, when you are taking the pairs of all these things, definitely I is not equal to J, and then the covariance now will become what? 0. So it is as good as now bearing in mind that the terms of all the covariances of the various terms in the models now will give us what? 0. Covariances of all the possible pairs of the terms in the model will give us what? 0, bearing in mind that this is 2. So I now have that here is what? Plus what? 0. Then we return back here now. What we have is now v of y of t is now given as. And I have to mention it here that the reason why I have theta 1 squared here is that the moment you are taking the variance of a constant, you square the constant and bring it outside the variance sign. So it is just like taking the variance of the whole of this, but squaring this theta 1 squared and bringing it outside the variance sign, and then taking the variance of that random variable. So here becomes what we call theta 1 all squared, sigma squared of what? A, plus theta 2 all squared, sigma squared of what? A, plus theta what? 3 all squared, sigma squared of what? A, plus plus theta what? Q all squared, sigma squared of what? A, plus sigma squared of what? Of A. This is true because we are told that the error term follows a normal distribution with mean 0 and constant variance, sigma squared. So the variance of error term at t minus 1 is sigma squared, at t minus 2 it is sigma squared, at t minus 3 it is sigma squared down the line. So the variance are constant over time because of the stationarity condition of what of the model. So in that case, what I'm going to have here becomes this is given as what? We open a bracket, we have 1 plus theta 1 all squared plus theta 2 all squared plus theta 3 all squared plus dot plus what? Theta what? Q all squared. Sigma squared of what? Of A. And this becomes what we call the variance of the moving average model of order Q. Okay? So that is how to get the variance of the moving average model of order Q. So what we are going to do is to quickly clean this, and then we look at what we call the autocovariance of the moving average model of order Q. So permit me to clean this. When you want to look at the moving average model, the autocovariance of the moving average model of order Q, what you are going to do is to multiply both sides of your model with y of t minus what? K. Okay? So that is the value of the series at lag what? K. So by that implication, what I'm going to have here becomes what? Y of t multiplied by y of t minus k for this side. The same thing is going to apply over here. So this equals, I have theta 1, a of t minus 1 multiplied by y of t minus what? K. Plus, I have theta 2, a of t minus what? 2 multiplied by y of t minus k. Plus, I have theta 3, a of t minus 3 multiplied by y of t minus k plus plus I have theta what? Q, a of t minus what? Q multiplied by y of t minus k plus. For this one, I have a of t multiplied by y of t minus what? K. Once you do this, you begin to look at it now. When k is equals what? 0, when k is equals to 1, when k is equals to 2, so that you will be able to see exactly what is happening to the model. When k is 1, anywhere is 0, so when k is equals 0, when k is equals 0. Anywhere you see k, you are going to put 0 there. So here becomes y of t into what? Y of t, because k has become 0. This is equals to what? Theta 1, we have a of t minus 1 multiplied by y of t plus. Here you have theta what? 2, a of t minus what? 2 multiplied by y of what? Of t. You have plus. Theta what? 3, you have a of t minus 3 multiplying by, you have what? Y of what? T plus. Plus, you have theta q, a of t minus q multiplied by what? Y of what? T. Then plus, you have a of t multiplied by what? Y of what? Of t. You are to take the expected value of both sides of this equation, and then taking expected value now, what you are going to have is e of y of t multiplied by y of t. That is e of y of t multiplied by e of y of t. This equals. When you are taking expected value of this, what this quantity means is that a of t minus 1 is multiplying y of t. And you already know that y of t is this. So if I'm using this a of t minus 1 to multiply this quantity, the only place where the error term shares the same time is at this first place where I have a of t minus 1. So, and then here now, I am going to carry theta 1 a of t minus 1 to multiply this. And I'm only interested where the error terms are going to have the same time lag. Wherever place they have different time lag, of course, it's going to result to 0. And in that case, I'll be interested here at this particular place, because here I have a of t minus 1, and here I have a of t minus 1. So here I have theta 1, here I have theta 1. So I'm going to have what is called theta 1 all squared e of a of t minus 1 multiplied by what? A of t minus 1. I will say plus. When I now come over here now to this particular one, I am using theta 2 a of t minus 2 to multiply y of t. And this is my y of t. And I will be interested where the error terms have the same time lag. So if I come here, it doesn't have the same time lag here because this is t minus 1 and this is t minus 2. So this is the only place where they have the same time lag. And here I have my theta 2, and because I have my theta 2 here again, it's going to be theta 2 squared e of a of t minus 2 multiplied by a of t minus what? 2. The same thing applies here when I'm having theta 3 a of t minus 3. I will land myself here. Then I have what? Theta what 3 all squared e of a of t minus what 3 multiplied by what? A of t minus what 3 plus. Then I will say dot dot dot. I will now arrive here, which agrees with this place. So I have theta what? Q all squared e of a of t minus q multiplied by a of t minus q plus. Then I will arrive at here, which will now agree with this place. Because here, this y of t now I have here contains this place. So I have e of a of t multiplied by a of t. So in that case now, what I'm going to have here is what we call the variance. So here becomes v of y of what? Of t. Because the expected value of the series at the same time lag will give you what we call the variance. So this will now be what? Theta 1 all squared sigma squared of a plus theta 2 all squared sigma squared of what? A plus theta 3 all squared sigma squared of what? Of a plus plus we have theta q all squared sigma squared of a plus what we have sigma squared of what? Of a. Which of course becomes the same thing as the variance of the model which we showed earlier, because we are told that the autocovariance of a model at lag 0, that is when k is equals to 0, returns the variance of what? Of the model. So which of course is exactly what we had before, that we can have it now to be this way. We have theta, we have what? 1 plus theta 1 all squared plus theta 2 all squared plus theta 3 all squared dot dot plus we have theta k q all squared close the bracket sigma squared of what? Of a. This was what we had earlier. Okay? So the autocovariance at lag 0 is the variance of the model, which one can see clearly from this. So we are going to show when k becomes what? 1, what is going to happen, so that we'll be able now to have exactly the general representation of the autocovariance. So you permit me to clean these ones. When k becomes what? 1, what I'm going to do here is when k becomes 1, then I will now have that anywhere I have k, it becomes 1. So I have what? Y of t multiplied by y of t minus 1. This is theta 1, a of t minus 1 multiplied by what? Y of t minus 1. This is theta what? 2, a of t minus 2 multiplying what? Y of what? T minus 1. This is theta 3, a of t minus 3 multiplying y of t minus 1 plus theta what? Q, a of t minus q multiplying y of t minus 1. Then plus I have what? A of t multiplying by y of t minus 1. Okay. So what I'm now going to do now is I am now going to take expected value of both sides of what? Of the equation. I will now take expected value of both sides of what? Of the equation. Okay? Permit me to remove what came on my screen. Okay? So what we are going to do at this point in time is to take the expected value of both sides of the equation. And taking expected value, I'm going to have that e of y of t multiplied by y of t minus 1 will now be equals. We are going to pay attention here. The attention we are going to pay here is we are using a of t minus 1 to multiply y of t minus 1. And another thing I want to remind us is this. If you express this one as y of t minus 1, let me show you something up here. Let me show you something up here. So we are discussing when k is equals to 1. If here is y of t and now we are talking about y of t minus 1, it means that y of t minus 1 will now be given as theta 1 a of t minus 2 plus theta what 2 a of t minus 3 plus theta what 3 a of t minus 4 plus you have theta what q a of t minus what q plus a of t minus 1. So if you have this, it will be written this way. But if you have this, it will be written this way. So we are careful now when we come over here. As I'm using this my a of t minus 1 to multiply this quantity, I will come here to look at a place where I have a of t minus 1. I don't have it here. I don't have it here. I don't have it here. Where I have it is here. And I know that when I'm taking expected value and then the error terms are not on the same timeline, the resultant, or what we call the result, will be what? Will be 0. So I will be concerned where I am going to get error terms that have the same timeline. Here is my a of t minus 1. This y of t minus 1, look at where it have a of t minus 1. So it is now going to be my theta. It is going to be theta here, 1. Taking expected value of a of t minus 1 and a of t minus 1 will now give me what we call sigma squared of a. Sigma squared of a plus. I will now come to this second one here. Here is now a of t minus 1. And here is a of t minus 2 and here is y of t. So I will now go for y of t and look at where I can get error term a of t minus 2. This is where I have a of t minus 2. So I'm interested only here. So here is my theta 1 and here is my theta 2. Taking expected value of a of t minus 2 and a of t minus 2 will give me sigma squared of what? Of a plus. I'm here. I am interested getting a place in y of t minus 1 where the error term is a of t minus 3. This is where the error term is a of t minus 3 at theta 2 here. So what I'm now going to do here now is to tell myself theta what 2, theta what 3, expected value will give me sigma squared of what? Of a plus dot plus. I will now ask us to look at this. If you find out that here is 1 and here is 2, here is 2 and here is 3. So this one is less than the next one by 1. So in that case, I am going to have theta what? Q minus 1 and theta what? Q for this particular place. Then I have sigma squared of what? Of a. Plus here is going to be what? Sigma squared of what? Of a. So what we are going to do is to tell ourselves that, of course, the autocovariance at k equals to 1 is what we call autocovariance at lag 1. So here is gamma 1 is given as. Then we now try to factorize. We have what we call theta 1 or sigma squared of what? A. You open a bracket. What will be left here becomes what? 1. Okay? Then, or we can even start it this way. We can start it from this direction. Do remember that here is t minus 1, y of t minus 1, and here is a of t. So if you express this, you cannot get a of t minus 1. So this variance that is here should not be here. Because if you expand this, you get this. There is no term of y of t minus 1 where you have this a of t. So taking expected value here is going to give us 0. Here is a 0. So you now come over here. So what you are going to have here becomes that you open a bracket. Here you have your theta 1 plus theta 1, theta 2 plus theta 2, theta 3, then plus. You have dots plus. You have theta q minus 1, theta what q, you close the bracket, you have sigma squared of what? Of A. So here is now the autocovariance at what? At lag 1. So we are going to now look at this and be able to generalize the autocovariance at lag k. So if it is now going to be autocovariance at lag k, you have that gamma k will be given as, you open a bracket, you have theta 0, theta 1, where of course this theta 0 is 1, such that if it multiplies this theta 0, so theta 1, we can come back to here. So we have plus. Here becomes what? We have theta what? 1. So we have theta k here. So here becomes, I also have here, so here becomes theta k plus 1. Plus, we have here theta k plus 1, theta k plus what? 2, plus, plus. We have what we call theta what? Q minus k. We have theta what? Q, close it, sigma squared of what? Of A. So, by implication, when k is equals to 1, of course, this theta 0, of course, is 1, and multiplied by this theta k is equals to theta k, and k becoming 1, we arrive at this. K becoming 1 arrive at this thing. 1 plus 1 arrive at this. K becoming 1, 1 plus 1 will arrive at 2. Here is 1 plus 2 will arrive at 3. Down the line. So this thing becomes what we call the autocovariance at lag k of MA of order Q models. Getting the autocorrelation is not difficult because, of course, the autocorrelation rho k is given as gamma k all over gamma 0. And of course, we know that our gamma k is given as this. And our gamma 0 was the variance that we had earlier. So it is going to be this quantity all over this quantity. What will cancel out now becomes what? The variances, which are found at the end of the expressions. And then every other expression in the terms of the gamma k remain at the numerator, and every other expression at gamma 0, which is the variance, remain at the denominator of the expression of rho k. And that's exactly how to go about obtaining the autocovariance, the autocorrelation, the mean and the variance of the moving average model of order Q. We are sorry for the change of the weather that perhaps made the view of the board very dull. It depends on my location. It came raining, and we apologize for that poor visibility that we experienced around here. Of course, if you have not followed or subscribed to our YouTube channel, please do subscribe, like and share our videos. Surely will keep coming your way with some of these things that are looked at as being difficult, making effort to simplify them for you and then improve your knowledge of mathematics and statistics. Thank you for your audience, and see you in our next class.